So far this week, we've taken direct methods that we already saw before, that previously were applied to dense matrices, and we showed how they could be modified so that they could take advantage of sparsity structure in matrices. And we saw that there was this relationship between the graph that explained the connectivity of in the domain and how that was related to the non-zero pattern in the matrix itself, or vice versa. Now, let's go back to the example that we started with the launch, the Poisson's equation and its discretization. Now, the equation that dictated that was going on, each linear equation, came from the fact that at any one point we were taking a linear combination of the points around it and then took into account also the value that came from the load at that point, the vector f, the function f. And that then gave us this equation right here, where if we then wrote that down for every point and we took into account the Dirichlet boundary condition, the fact that on the boundary the function was equal to 0, then we ended up with this sparsity structure right here. Now, we can take that equation and we can also rewrite it as 4 times epsilon I is equal to, and then bring everything else to the right hand side, which is what we get right here. If we go back to the domain, what this here tells us is, well, maybe we can come up with a method where at each point we simply take, well, if you divide this into all of that, it's sort of like taking an average of the points around it plus the load. So what if at each point we just say, let's replace that value with this averaging of the points around it, and let's do that for every point, and let's just keep doing that until the iteration, the method stabilizes into something where it doesn't change anymore. And once it doesn't change anymore, it doesn't change anymore because the averaging that you do of the points around it is exactly the value that you already have there, which means that this equation is satisfied and therefore you have converged to an actual solution. Okay, so that's the idea. Now, the way you can say that is, well, if we update all of these values all at the same time, then what we really are doing is just this matrix vector multiply with this sparse matrix here, adding that to this vector right here, and then dividing by 4 right here. All right? And lo and behold, you actually saw in the launch that this works. All right, so how can we sort of say that? Well, what we really are saying is, if you think of these values all as the values after k iterations, then this is the value after k plus 1 iterations. And we're doing that for all of these values simultaneously. So we've collected all of the values for the k plus first iteration over here, and so forth, and all of the values for the kth iteration right here. Okay, now, does this converge? You could probably give a physical reasoning why the physics tells us that it should. Be nice to give a linear algebra explanation of why it happens and when it happens. It would also be nice to sort of do this more generally for matrices, as opposed to doing it just for this particular example. So how do we do that?